Hi friends, today we start lecture 73 on helicopter dynamics, and today I'm going to discuss plate bending stresses and their calculation for typical helicopter rotor blades. I am Dr. Ranjan Ganguly. Now we know from mechanics of materials that the first step to calculate bending stresses would require us to calculate bending moments, and from this bending moment expression we can actually calculate the bending stresses. Now, there are two methods of calculating bending stresses in helicopter dynamics which are popular. The first one is the modal method and the second one is the force summation method. So, I'm going to discuss both these methods next. Now, let's start with the typical problem and split this deflection which we have obtained using some method into two parts. So, one is a spatial part which is yi function of r, and the second is a time dependent part which is qi into t. Now, here we are assuming that we have solved the response problem, that is, we have solved the system mq double dot plus cq dot plus kq is equal to f of psi, and therefore at the end of this solution procedure we have this solution in this particular form. Now, in many cases, if you are using a method such as a Galerkin method, your gamma I would be known, your qi would be known. These may, for example, be some displacement you have selected or the mode shape. However, if you are using the FEM method, you have to essentially extract these from the eigenvectors for the problem. So you would have the global degrees of freedom, and then using the shape functions you can actually get this particular function out for the entire global system. Now essentially here we are going to consider n terms, so here I is 1 to n is given. Now the deflection is known here and we need to find the bending stresses. So we resort to our well-known formula. Now the bending moment at a section is given by mr is ei into the second derivative of w. And what we do is we take this expression here and we plug in our expression for w in terms of the summation here. So you can clearly see that the second derivative of the function or the value y is taken here. So that's the expression for the bending moment at a given section. Now the bending stress at this section would be given by sigma is mz by I, and therefore you can use this expression here, substitute mr from the first equation and get the bending stresses for the corresponding problem. Now the bending stresses are proportional to displacement. So you can clearly see here that the bending stresses would be proportional to displacement. Now this method which we discussed is known as the modal method, and it is often used in many helicopter codes to calculate the bending stresses. Now let us look at some aspects about this modal method. First is that you are going to need many terms in this series to obtain the bending stresses correctly. So that is the sigma I is 1 to n, the value of n should be pretty large. Now the modal method is simple but can result in poor results if this number of terms in the series is low, and the reason is that the error in the solution increases because we are taking the second derivative of the mode shape function, and this essentially will amplify any kind of numerical inconsistency which is present in this solution. So one of the ways to enhance the modal method would be to use a better function. For example, the mode shape can be used, but typically mode shapes of the non-rotating beam can be used, or even a rotating beam can be used if it is possible. So mode shapes differentiate very well and therefore the results will be quite good. Now in general we can see that one of the reasons a lot of effort is expended in rotor dynamics to calculate the displacement profile very correctly is that the calculation of stresses is very important. And the calculation of stresses being very important, the displacement calculation is extremely important, because very often, like in the modal method, the stresses are coming by differentiating the displacement, and that also differentiating the displacement twice. Now, the second method, which is often used to calculate the bending stresses, is known as the force summation method. So here what we do is we take the blade, we take a section, and we figure out what are the forces which are acting on this section, or the small piece here, which is given by d rho. Now this is at some distance rho from the center, and let's say there is one more location r here, and we want to know the bending moment at this station r, that is m of r. Now this is going to be essentially the integral from this small r to the end of the blade, which could be capital R, which is the blade radius, and then we sum the forces. So we have the Fz force acting up, we have the Mw double dot force acting downward. So these two net forces are here. The net force is Fz minus Mw double dot. This is multiplied by the distance rho minus r. So that's this distance here. That's the moment arm at this point here. Also, there is a force because of the centrifugal forces. So you can see this centrifugal force is acting in this direction. So this force was going in this direction. So its direction we have taken as positive. So this is in the reverse direction. So this is negative. And here the moment arm is going to be W of rho, which is the displacement at this point, minus W of r, which is the displacement at this point. So this distance is the moment arm for the centrifugal force, and then we take this and write it out. Now essentially at this point we would have known Fz, we would know W, and so on. So here of course the displacement is being taken with respect to time, so that's different from with respect to space as we did previously, and so in many cases the force summation method may be better if your W double dot is quite accurate. So we see in the force summation method that some of the problems which are present in the modal methods due to double differentiation of the spatial component of response get mitigated, and the moment at a section R can be calculated like this. So we have a formula here, we can use it and calculate the moment at force summation method, and then once the moment is known from the previous formula which we listed, we can actually calculate the bending stresses. So that's the way to calculate the bending stresses here. Now, since integration is involved, this method will give you better results. So that's something to keep in mind. In general, in mathematics, whenever you differentiate functions, the errors which are present tend to get magnified. And whenever you integrate functions, the errors which are present tend to get mitigated. So that's something which we use here. That's something which is important in numerical analysis especially, and we need to keep that in mind. So I will end this lecture here, and I will see you in a video sometime soon. See you then.